Looking at organic compounds. The word organic is in the news quite a bit. People are saying grow organic or they buy organic foods. That's not what we're talking about here. We're talking about a very, very specific type of chemicals or group of chemicals. So all compounds can be classified into two categories. You can classify them, everything is either, your pen, organic, or the fancy word is inorganic. And although this may not sound very profound to you, this is what explains why you are all here. How all of the chemicals in your body can combine together to form a human being and a person. Okay? There is a fairly easy way to recognize the most organic compounds, and probably this year you'll recognize any organic compound this way. They contain, Mr. Do It, carbon. Carbon is an extra special element. It's the element of life. If carbon didn't have the properties that it has, none of you would be here. Neither would trees, neither would plants. Everything is carbon-based life forms we talk about. So organic compounds contain carbon and usually contain hydrogen. Inorganic compounds do not contain carbon. Now, there are a couple of exceptions. Not everything that contains carbon is automatically organic. But thankfully, Kenzie, most of these you've already seen before in your young science career. In fact, we talked about one just a couple of minutes ago. We said something dioxide. What was that? Okay, CO2, carbon dioxide, is not organic. Also, carbon monoxide, CO, is not organic. Carbides, those are the ones that contain CO3, that carbonate that we just looked at a couple of minutes ago, are not organic. They all contain carbon, but they are inorganic. So for you folks, Hayden, aside from those ones, if it's got a carbon in it, especially if it starts with a carbon, it's an organic chemical. I can't say anything with carbon is organic. What I can say is almost everything, and I just gave you the key exceptions in Science 10. In fact, well over half of all the known compounds in the universe are organic. Why? Because of the wonderful properties of carbon. You got your pink periodic table handy? Look at carbon, and you may notice that carbon is missing something that all of the other atoms have on them. What's carbon missing? And this is done deliberately. So it's in the top row. It's element number, what's carbon? Element number what? 14? 14. Find it there. Huh? Doesn't have a charge. But boron isn't quite as nice as carbon. It's one of the few elements that does not have an ionic charge. And the reason is it almost never, again, I can't say never because there's exceptions to every rule, Amber, but it almost never forms ionic bonds. If it bonds, it's going to bond covalently by sharing electrons. Okay? Now, it can be part of those polyatomic ions. Those are the ones on the back of your pink sheet in that chart there. But remember, those polyatomic ions, those are all covalently bonded, and then as a group, they'll bond ionically. But it doesn't form covalent bonds hardly at all. So the atoms in a polyatomic ion are covalently bonded. What are the polyatomics? They're in that little chart on the back of your pink sheet. Any of those that have carbon in them, the carbon in there is covalent. How many, the next line says, carbon has blank electrons in its blank shell. How many electrons does carbon have in its outer shell? And how can you figure that out? Start counting from the left, move across. 1, 2, skip, 3. How many electrons does it have in its outer shell? 4. What was the fancy word for outer shell that began with the letter V? Let's use that just to review our memory. And do you remember how many electrons did you need to completely fill up that shell? How many? 8. How many does carbon have? It's exactly half full. That's why it's special, because 4 electrons is a little bit too many electrons to gain or to lose, which is why it's really not going to do ionic bonding. It's going to bond covalently. So too many electrons to lose or gain, so it shares electrons, which means it has to form covalent bonds. How many electrons does it want to gain? 4. So how many bonds would it need to form? How many electrons does it want to gain? 4. How many bonds will it need to form then? It's going to need to form, it's going to need to go form 4 bonds. But it can also form 2 or 3 bonds to one other atom. These are called double or triple bonds. This is why carbon is so flexible. It really bonds, Sarah, with almost anything, and you can customize it. We have the technology now where we can create carbon chains of the size and type and property that we want. It's got a preference, though. It's a little fussy. Usually it will bond with atoms that are close to it on the periodic table. So if you got your periodic table in front of you, what atoms are close to carbon? Nitrogen. I got that one listed right here. It really likes oxygen. Nitrogen it likes an awful lot. Sulfur. Missed the L, Mr. Duke. Sulfur. The bond with phosphorus. It'll bond with the halogens. What were the halogens? Do you remember on the periodic table? Which group is the halogens? 18. Group 18? 17. Isn't it row 17? Row 17. And here's the other handy thing. It can also bond with itself to form long chains. All oils, all plastics, these are all polyatomic chains of hydrocarbons, of carbon and hydrogen and oxygen. Or complex ring structures. In fact, no other element can form as many stable compounds as carbon.
So that's why they make plastic bags out of oil?
Yep. They don't make it out of oil. The fact that oil has carbon in it is why we can use oil. I got to go one step further. The fact that oil is so carbon-based means, oh, hey, it's a liquid with carbon. We can make lots of stuff with it because carbon likes to bond with stuff. In fact, even more basic than that, that's why that we are all carbon-based life forms. When you burn wood on a fire, that black stuff that's left behind, that's carbon. Okay? When you burn plants, same thing. When our bodies decay, when we pass, when we die, same thing. We are carbon-based life forms. Why? Because carbon likes to bond with all sorts of stuff, but it bonds covalently, which means those are very, very strong bonds. Ionic bonds are very easy to break apart. If you give me table salt, I can dissolve sodium and chloride into water, and I can break the bonds just by mixing, by stirring. If you guys jump into water, do you dissolve and come apart? No, because your carbon, you are covalently bonded. You okay there, folks? Yeah? Okay. So, because organic compounds get so huge, because organic compounds get so huge, they're very tough to visualize. We tend to represent them in certain ways. The first way is in what we call the molecular formula. This is the way we've been doing so far this year for most of our other stuff. Can I get this? There we go. It's simple, but it doesn't show what it looks like or how the atoms are joined together. For example, CH4. How many carbons? 1. How many hydrogens? 4. But what shape on the molecular level do they form? And it's that shape that really defines a lot of what that quantity, what that compound's properties are. So molecular formula, nice, short to write, has its limitations. Next page. Oh, by the way, before you turn the page, CH4, methane gas. Methane. Blows up. Okay. There's a second way that we can show these, and these ones I find kind of the clearest. This is what's called good gosh, Mr. Duke, spell it right. A structural diagram. A structural diagram. Missing a T. Structural. There we go. Structural. Structural diagram. Psst. And what this does is it shows some parts of how atoms are joined. The problem is when you draw it on a flat piece of paper, Hannah, it's very tough to show that actually these atoms have 3D. They're not just flat, they point up and down, which is tough to draw on a piece of paper. But here is an example of a structural diagram. How many hydrogens do you see? Count. 4. How many carbons do you see? This is CH4. This is methane. Now, how many bonds does carbon need to make? 1, 2, don't write this down, 3, 4. So what we have here is hydrogen wants 2 electrons in its outer shell. It's supplying 1 and sharing 1 with carbon. This hydrogen is supplying 1 and sharing 1 with carbon. This hydrogen is supplying 1 electron and sharing 1 electron with carbon. This hydrogen is sharing 1 electron and sharing 1 electron with carbon. Oh, and can you see how many electrons does carbon have now? All 8, it's happy to. There's a third way. This is the best visual way, but it's very, very tough to draw. It's what's called a, of all things, wonderful name, ball and stick diagram. Little tinker toys. You can actually buy these, and you can start to model some of these organic. You have those? Yep. They're fun. You know what, Josh? It shows the 3D great, but it's really hard to draw that. I had to steal that from a computer diagram. I was going to try and draw it by hand. No. But you can see, I hope, Hannah, when you look at this particular diagram here, that, you know what, it's not flat the way this is. This shows them all flat with a 90-degree angle between them. Actually, no, it's much more complicated than that. One's pointing up. They kind of form a triangle in between each one. And the last one is called a space-filling diagram. It shows the electron density, but it's hard to draw or model physically like that. Brendan, you need to know the difference between all four. Now, some of them are pretty easy. Can you figure out how you can remember the ball and stick diagram? Because it's got a ball and a stick. Okay. I think you can figure out which one is a molecular formula because it has just a formula. Then the difference between the structural and the space filling, I remember this is a space filling diagram because look, those things are filling up the space.
Isn't it structural to Lewis?
Pardon me?
Isn't it structural to Lewis?
A structural is a modified Lewis diagram, yes. Yeah. Do page 245. Am I going to assign page 245, Mr. Dewick? Can you all turn in your... nope, I'm going to skip that, actually. So let's take that. Less homework for Kenzie. Turn the page. Okay. Yeah, lots of terminology. Continue. So we've talked about how you recognize an acid. Starts with an H. How you recognize a base. Ends in an OH. How you recognize a salt. Well, it's not an acid or a base. Okay, how can you recognize an organic compound? The first way is easy. If it doesn't have carbon, it's inorganic. If it does have carbon, it is organic. Oh, okay, Amber, except for as a carbonate, CO3, as carbides, like where carbon is on the very, very end of an atom, not at the very, very beginning, it's being bonded, or as oxides, CO2, CO. Okay. Now, a lot of organic compounds have a hydrogen in them. So we decided this. The H is not written first in organic compounds. Why? If the H was written first, what would we think it was? Acid. So to distinguish it from acids, where the H is first, even if we have an H, if it's an organic compound, we'll put the C in front of it. We'll put the C in front of it. Okay? Hydrocarbons. What's a hydrocarbon? What do you think a hydrocarbon contains? What do you think a hydrocarbon contains? Hydrogen carbon. So it's in the word. Contains, I got to add one more thing though, only hydrogen and carbon. Nothing else. But there are thousands of hydrocarbons because carbon can form long chains. Okay. The simplest one is methane or methane. It's pronounced both ways. Why is that the simplest one? How many carbons does it have? No. How many carbons does it have? One. Then we go up from there. Oh, you know what? Here in this chart are the first 5 hydrocarbons. You have methane, CH4, structural formula, shortened structural formula, space filling model, and that's used in natural gas heaters. Oh, and then there's ethane. Add an extra carbon. Psst. Can't believe I didn't notice that earlier. Oh boy, I'll take it away from you next time. If you add an extra carbon, oh, how many bonds does carbon want to have? Do you remember? 4. So if I add an extra carbon, I can go 1, 2, 3, and then they'll share one, and then this guy here has 1, 2, 3, 4 bonds. That's what that one would look like. Ethane is used in manufacturing plastic. Propane. Hey, where do we use propane? Barbecues. Okay, camp fuel. It looks like this. It's C3 and 8 H's. Butane. Where do we use butane? Handheld lighters and some curling irons. Pentane.
Also in powdered non-liquid shampoo.
Okay. Pentane. 5 carbons. Looks like this. As a structural formula, this is how they can show you it's a C with 3 H's, a C with 2 H's, another C with 2 H's, another C with 2 H's, and a C with 3 H's. Can you see how you can get that shortened structural formula from the picture there? They're just rattling off the C's. That's used in gasoline. Now here's the first pattern I want you to notice. Can you see any kind of a relationship between the number of carbons and the number of hydrogens? The number of carbons and the number of hydrogens. The number of carbons and the number of hydrogens. Can you spot a pattern? In other words, could you guess what C6 would go with? H what?
14.
Convince me.
The 4, 6, 8.
Can you, okay, what if I told you what would C10 go with, so I didn't let you fill in the rest of them? Can you find a way to get there directly?
What?
You spotted the pattern. You said, okay, 5 goes with 6, and these are going up by 2. What if I didn't give you the rest of them in the middle? Can you find a way to get there directly?
Oh, okay.
Can you find an equation that when I put a 5 in it, gives me 12 as an answer? When I put a 4 in it, gives me 10 as an answer. When I put a 3 in, gives me 8 as an answer. Anybody spot it? What's 5 times 2?
10.
What do I have here? 12. What's 4 times 2? 8. What do I have here? 10. What's 3 times 2? 6. What do I have here? 8. Anybody spot it yet?
22 hydrogens?
Pardon me?
22?
22? Convince me. Tyson, you are right.
Because you just take the carbons, like the next one up, so like 11, and then times it by 2.
Or double this plus 2. It's the other way. Double it plus 2. Double it plus 2. That's another way, Sarah, to get your 14. If you double the carbons plus 2. Let's go back to here. You can keep adding more carbons. I showed you the first 6. Oh, they go on forever and ever and ever. But they're used all over the place. Certainly you all see where these are used in gasoline and fuels. We use them all over the place. They burn good. And they're a controlled explosion. They burn not so fast like the alkali metals where you're going to damage stuff. Nice and slowly, we can control that. Ooh, we like. Oh, they also pollute. We'll come back to that in a bit. So these compounds are used as fuels. When you burn them, they combine with oxygen. The hydrogen burns, the carbon joins with oxygen to produce greenhouse gases. Oh, what's CO2? What's the fancy English name for that? Carbon dioxide and H2O, water. The larger the molecule, the more easily it becomes liquid. So we don't use methane, natural gas. You can liquefy it, but it takes a lot of pressure. Ethane, we don't use that much at all to liquefy either. Propane in the propane tanks under pressure is a liquid, but butane and protein we can liquefy fairly easily, which is why those are our fuels of choice for tanks. Oh, and pentane is actually liquid at room temperature. That's why it's used in gasoline, because gasoline needs to be liquid at room temperature. So, methane, ethane, propane, butane are gases at room temperature. But propane and butane can be pressurized into a liquid. And pentane is already a liquid at room temperature, and anything bigger than that is also a liquid at room temperature. Okay. Can you turn to page 247, please? I wrote down reading check, and I said write your answers in the space below. We're just going to do them orally, and then I'm going to stop. You can write down the answers if you want to, but let's see if we can just get these from what we've learned so far. You have a textbook? Okay, put that one back when you're done. 247. So the first question says, boys and girls, what element must be present for a compound to be considered organic? Carbon. Okay, that you got to memorize. Sorry. What other element is almost always present in an organic molecule? Almost always. Why not always, Mr. By the way, there's exceptions to all the rules that I'm giving you. As soon as we go further down the periodic table, things start acting really, really weird. That's why we're sticking around mostly at the top. Number 3, list 3 carbon-containing compounds that are inorganic. So what are 3 compounds that contain carbon? Yeah, you do. That are not organic. CO2, carbon dioxide, and CO, carbon monoxide, and CO3. Oh, I can probably, if I can remember that carbon dioxide is inorganic, I think I can probably get my brain to trip into the other ones. Okay? Question 4 says, list 3 inorganic compounds that don't contain carbon. List an acid or a base or almost anything else. I'm not going to even... NaCl, table salt. HCl, hydrogen chloride, that was hydrochloric acid. All sorts of other ones. Oh, and the key one, number 5. What 2 elements are present in a hydrocarbon? How can you remember that those are present in a hydrocarbon? Okay, you okay with that? We will press pause. We will leave you wondering because some of you want to find all about our next topic, which is alcohol. About 10 of you. So, huh? So, what's your homework right now? I'm going to pause the video.